right, so I'm going to demo. This is oh boy, this is the doc file associated with with um, lecture 2. Okay, and I have this one open because it explains how I built it. Okay. Um, uh, so I downloaded TivaWare. Okay, TivaWare is that stuff that we didn't let you use in 319K or 445L, but it basically is an entire set of drivers for the TM4C. Okay, and in particular, I'm going to use a TM4C 1294 because it's, as you can see, it's got an Ethernet jack. And I basically, that's a picture of what I have. Okay, because of the cabling, it's off to the left. But this is exact. I don't know if you can see there's the thermistor sticking out. Okay, that's the thermistor that's sticking off of this cable right there. On this board here is basically a 445L temperature instrumentation bridge and analog filter. The cool thing about the TM4C 129 1294 is it's probably the only TM4C that will survive the purge because it's essentially been rebranded as an MSP part. 432E. Okay. And as far as I can tell, it's exactly the same silicon, and all they did was change the sticker on the top of the device. The big red board here has one pin, which is different between the 129 TM4C 1294. And so when Texas Instruments purges the TM4C line, because that's what companies do to make money, you'll probably be able to rerun your old TM4C 123 code on an MSP 432E. But okay, so that's my physical hardware. There's an Ethernet cable, and I just got it plugged into my router. Actually, not a router; it's a switch. Okay, because the router's downstairs, so the house is full of crap. And then this is the end point. Okay, so Alt-Tab. Okay, where's the actual internet? Where'd it go? Oh, here, internet. Oh, here. I don't know. It crashed. Okay, there it is. Okay, so as you can see, there's a whole bunch of things listed in my home network, everywhere from the television to the dozens of computers all piled around. But this is the local subnet address. When I plugged the system into the switch, it negotiated a subnet IP address. Okay, so that's this guy here. Okay, temperature. Okay, so I'm now putting zoom your eyes into this spot right here. I'm going to just put my fingers on the thermistor. I'm going to get warmer. You can see it's 30 something degrees. Okay, going back to this guy. How I did it is this is a server, right? So when the laptop wishes to fetch a page, it does, the laptop's the client, the TM4C 129.4 is the server. So this C code here is running on the embedded device. And when the laptop requests a page refresh, it gets this HTTP code. It gets this web, this HTML code. And so on the TM4C is a bunch of software which produces HTML code and sends it back as a response to the client. So again, the what you call it, the server is measuring temperature down here down here in block 2. Where'd it go? Block 2, right? Board update right here. Fixed page. Right here, it measured temperature. Well, this whole thing. It measured temperature from the A to D converter, converted it, the raw data to fixed point data. That's a 445L question. Converted it to a string, and then stored it into this part of the web page. So these 5 characters right there are being replaced every 5 seconds. Yeah, so there's the size of it. And the rest of the web page, the first part and the third part, are fixed. Okay. And so this is the code. Basically, all I did was write this part of the code. This is pretty much all I wrote. The rest of it was plug and play. And yeah, so again, I got it from TivaWare, and I'm running this guy here. This is a starter code for from Texas Instruments. All right, let's show you one more thing here. Okay, show you putty. Okay, so what I'm going to do is I'm going to reset the controller. Okay, I'm going to, I don't want to power it down where my putty will quit, but I'm going to hit the reset button on the device, and you can see it established a link. It got a an IP address from the switch. Okay, and now this crap is it's sending it's the client is requesting a packet, and the IoT device is sending the packet back. So every 5 seconds, this is a debugging log. But Ethernet's, if I'd opened up a port on my router and forwarded that port to this thing would have been internet facing, but obviously that's a security risk, so I didn't do that. Questions on this demo? I mean, it doesn't fit the paradigm of the rest of the class because it's wired, but nevertheless, Ethernet could be an IoT device. So if you had an application where there was already Ethernet in the room, and you could bolt it down, it's obviously got the advantage of being fast, and all that crap about interference with the other things in the room is good. This will be an interesting thing. Has anybody built a house recently?
No.
No. Okay. My son, who's, he's 35, had a house built, about 2 years ago. It's one of those developments in Florida where all the houses look the same, but that's okay. But he paid the builder to fill the house up with Ethernet cables because, and it's interesting to imagine what life is going to be like 20 years from now, right? It may not, Ethernet may be obsolete. But he did say, well, don't worry. They put in the house, they put in tubes along with the Ethernet cables, so that if you could basically take one end of the string, tie another string onto it, and pull a different kind of cable through. So he says when we update the fiber optics, he'll be able to redo the house in fiber optics. Anyway, so it's interesting to imagine what the future is going to be like, right? All right, that's enough of that. Okay, shut this off, pull that out. Okay, let's go to session. All right, T. Okay. So we're going back to wireless. Oh, I didn't upload this. I'll upload all these files. So now we're doing 802.11, and this covers both the personal area network and the local area network. You know, it's basically going to be a personal area network if it's closed and no one else but you and your buddies in the room can access it. You can still use 802.11, but if it has an outward facing port, the router streams onto the internet like we had in the last slide, last deck, then it becomes a local area network. And again, W stands for wireless. The eventual lab we're going to get to has a CC3100 in it. This particular, I'll have some demos to do, not today, on the 3100. The 3200 is a more powerful chip, or the 3120. This was the last wireless chip, that wireless board that TI made that didn't require TI RTOS. And so it not only required TI RTOS on the 3100, it required TI RTOS on your TM4C or your MSP432. So not being a great fan of TI RTOS, I balked, and whenever I use TI chips to do Wi-Fi, I use this one because it doesn't require your master controller to run TI RTOS. Nevertheless, we're not going to talk about this chip today. We're going to do the usual stuff: frequencies, the stack. We'll revisit the modulation, and this particular deck talks about the physical and the media access layer. All right, so here's the stack once again. The only difference here is the physical layer, and boy, what this does tell you is that this is a very complicated. This is an example of a field that changes a lot. Okay, so I don't know how people make money in this business, because when you make yourself a chip, you got to support all these stupid protocols, A, B, G, N, A, C. There's another slide with all the list them on there. And so, although there was a nice comment in the book about the advantage of stacking or layers. Okay, and this is I guess something to remember forever. What's the advantage of layers in general?
They only talk to the surrounding layer.
Well, that's a definition of a layer. The layers only talk to the layer above it or below it. But what's the advantage?
It's easy to
Data
swap them out.
abstraction.
Yeah, swap them out. So the whole Wi-Fi life was built on that. That's the success story of Wi-Fi was built on that fact that it had the advantage that if you wanted to take an Ethernet physical, wired network solution and make it wireless, all you had to do is change the physical layer. Now, it's a little bit of MAC layer changing too, but all the other layers, the TCP IP layers and the FTP layers and all those other layers, did not need to be redone as long as you match the interface. And so they made a nice story about how when Wi-Fi came in, it really burst onto the scene in a very powerful and successful launch because of the layered protocol. So yeah, so, and you can sort of see it here. And as Wi-Fi itself uh, uh, evolves, right? So this is an example of an evolution um, between as you try to get, up to a gigahertz, right? We want a billion bits per second with 802.11 AC. It basically just replaced the physical layer. Okay, so that was a success story here. And you can't read this slide, but you got the book, or if you don't have the book, you can zoom into this slide and sort of escape. Zoom into this slide. They were nice to give me this deal about this is basically an evolution of 802.11. Okay. And I was all excited when we got G, first got G, it was faster. And then we first got N. We're going to talk about N. That's probably all that I got here in my house. But obviously it's been a while since I bought Wi-Fi. A lot more standards have come up. Okay. And then for each of these things, it talks about the modulation. So they have different modulations. There's only a couple of frequencies in here, and that's 2.4 and 5 gigahertz. Most of these are either 2.4. Well, it looks like there's some that are others. This one you probably know the answer to already without looking at the rest of it. This gray one here, this is the frequency, 460, right, 470 megahertz. What's that for? What would be the advantage of a Wi-Fi physical layer at 470 megahertz?
Range.
Range. Okay. And so this will be a long range. What's the other advantage? And what's the disadvantage? Okay. So range is good. There's one more advantage and there'll be one more disadvantage.
Penetration.
Well, that's the same. Okay, right. Range. Okay, sure. Penetration is good. It goes around objects way better. Yep. So it's a Wi-Fi protocol down in the sub-gigahertz, world, right? That's what this line of gray is. So yeah, we'll go through walls better. Sure. Yeah, that's another advantage.
Are you looking for bandwidth is lower?
Yeah, that's the disadvantage. Bandwidth is lower, but what's an advantage? Okay, whoops, over there. Low power is an advantage. Run slower always makes less power. Okay. So yeah, I don't know. It's a crowded space. Okay. Here's some terminology in Wi-Fi. Stations are your endpoints, things like your, I don't know, your laptop, your phone, your television, your television, your refrigerator, your washing machine, your car. Those are typically stations. And then we'll see there's the access point is either the switch or a router, depending upon. See, I thought my space was crowded. Having, I don't know, 10 things, 20 things in the house that are wireless. Apparently, there's still some room to grow. The book says you can have 2,000 of them. So this is the basic configuration: a single access point with multiple endpoints that all communicate to that access point. So obviously, if station 1 is talking to station 2, it has to go through the access point. If station 3 is talking to the internet, it has to go through the access point. But if you can configure it is a station. Now this is actually, it's not one of the labs that I had created, but this was the mode. This was one of the modes that that Sarab, the grad student working with McDermott, on that big purple board, or what some people did with the ESP 8266, is to create a peer-to-peer network without an access point. So this is an example of a personal area network using Wi-Fi. Okay, and so the in this configuration, I don't have a lab that does this, but all of the Wi-Fi chips do this mode where you're not connected to the internet. You're basically creating a subnet within the using the protocol. So there's no particular access point for which you connect to. But that's a fun use case if you've got a solution that you how is this different than Bluetooth, by the way? Which is Bluetooth is another personal area network.
Does this support more multiple connections
Yeah,
at the
so
same time?
yeah. So there's no client or server here, right? They're all whatever you want. They're all the same, basically. So yes, you could take an ESP 8255 or a CC 3100 and make it be the access point. So this access point here could be implemented with one of those Wi-Fi chips, ESP 8266 or the CC 3100. But in independent mode, you don't have an access point. You can just sort of group them together. And obviously they got to be close enough to hear each other. But then if you take two of these, take one of these, well, you take two of these, right? And so if you have a system with two access points, okay, and then allow the access points to talk to each other, either by Ethernet or wireless, okay, then you have this distributed system. So basically two or more basic systems. And so a lot of large, when you buy your large house, I don't know if anybody lives in a large house, your access point may not be strong enough to reach all parts of the estate. So if you have a access point in the garage and have an access point in the barn and have an access point in the second floor and have an access point in the kitchen, and then you somehow connect them all up together, that's what this distributed system is called. So they're all part of a system, but it has multiple access points. And that's obviously interesting when you have more than when you can't reach them all. All right, so here are the frequencies. As you can tell from the number of protocols, there are a number of ways in which these frequencies are carved out. Okay, so here's some of the simple ones. We actually saw this particular slide when we did Bluetooth. When we did Bluetooth, we saw this slide. Well, at least we saw some of it. We saw we saw it as a bad thing. This one, okay. Back in the Bluetooth world, we saw that channels 1, 6, and 11 was one of the use cases of Wi-Fi, and it overlapped with the BLE. And so to remember this BLE slide, okay, Can you remember that in your mind? And then go over here. Okay, so that was now I got to remember it. That's 1, 6, and 11. Okay, so you had 1, 6, and 11, but now you can sort of see that 1, 6, and 11 aren't the only channels that might mess up your Bluetooth, right? So if somebody happens to be on channel 9, that will affect some of the Bluetooth. And so what was when we did Bluetooth, what was the solution for, well, how did Bluetooth survive in the presence of Wi-Fi?
Frequency
Simpler.
hopping.
Yeah, just went to go. It hopped around looking for a place that worked. Okay, and so how do you imagine Wi-Fi is going to survive in a crowded space with Bluetooth? It's going to frequency hop. Okay, not in the same way, but it will still frequency hop. Okay?
Does I talked to this old timer at the park, a ham radio guy yesterday. It's just a weird aside to ask this question, but he was basically saying you only need a certain amount of power to talk responsibly. Otherwise, you just crank up the power and you can overwhelm whoever else is talking on that channel, essentially jamming. I mean, can Wi-Fi prioritize? I guess prioritize itself because it has more power.
Yeah, you can clearly be a bad actor. It's obviously against the law to jam the channels, but if you crank up the power, yeah, or spread your system across the entire space. One of the ways in which the military does secure non-jammable communication is the software-defined radio, which allows you to jump all over the place. So you're not only in this narrow band, 2.4 gigahertz, you're in a bunch of bands, and they basically can't jam them all. Okay, there's so many channels out there that they in order to prevent the enemy, so to speak, from jamming all of their stuff, they basically hop a lot, and they never stay in any one place too long. But yeah, no, it's clearly you can. Most in my experience, most of the problem exists when there's just too many telephones and too many computers and too many things in a conference center or a airport or someplace where there are a lot of people. Okay, so there are some in modulation schemes that are new and some modulation schemes that we've seen before. And so remember there was about 10 or so different 802.11 protocols. The N protocol uses and there's a definition of direct sequence spread spectrum on a subsequent slide, and a definition of orthogonal frequency division multiplexing in another slide. But the point is here, G uses one and N uses a different one, and then but this is showing you the frequency overlaps for the various channels for these three different protocols. If you remember, if you're running a 2.4 megahertz, 20 megahertz per channel means the width, right? The width of the channel. Okay. And here's a review. We've actually seen this slide before. This kind of thing is on the test on Tuesday. The amplitude shift key basically adjusts the amplitude. The ones are a different amplitude than the zeros. The frequency shift key basically takes two frequencies. They're not this different, right? They're both frequencies are in the band, in the channel band. So this is an exaggeration. And then oscillates the frequency. And then the phase. And again, the thing you want to remember from the thing you want to remember on the quiz about phase shift keying is what? That this particular picture illustrates the wrong way to do it.
Discontinuities?
Yeah, discontinuity. So the really all the fancy phase shift keying is to allow you to shift phase without having those discontinuities, which cause weird, obviously spreads the frequencies way out beyond your stuff, which requires higher, Q filters to remove. But that's an overview of some of the three basic types of, and we're going to do another one, and that's a combination of amplitude and phase. Okay, so this is a combination of amplitude and phase. So if you look at the XY plot in polar coordinates, okay, so think of each of those. Think of the circles here. Yeah, come back. Come on. Draw. Can't draw. Not letting me draw. Anyway, think of these circles as a character, a communication chunk, right? And this particular node represents 4 bits of data. And those 4 bits of data are in polar coordinates. You can think of the 2 parameters are amplitude and phase. So the inner circle is a lower amplitude and the outer circle is a higher amplitude. Now, this is an example so when I show you this, I'm going to ask, when I give you this on the exam, I'm going to say, what fundamental principle does this embodiment of amplitude shift key contradict? On the exam, when I show you this picture and say this example of amplitude shift keying violates one of the fundamental principles of communication.
There's no energy transfer when it's
during the zeros there's no energy transfer. Okay, and you can see how they solved it here in this one, right? This is a combination of amplitude modulation. See the picture on the right. There's 2 different amplitudes, a big one and a small one, but both of them have energy. Okay, but in order to encode more bits, why do they encode more bits per character?
Because now you're shifting both phase and amplitude.
Yeah, but why do you do both amplitude and phase?
So you have more combinations. So you have
Yeah,
more.
so why do you, and if you have more combinations, okay, you probably, it's sort of a duh answer to my question. What am I doing here? I'm increasing what?
Your bandwidth.
Bandwidth, because
data rate.
my frame rate is constant, but I have more bits per frame. Okay, so this is a 16 QAM, but there's a 64. That's not 64 bits, that's 64 choices, 6-bit. And what's the advantage of it? More bandwidth. What fundamental theorem puts a limit on how many bits I can send per frame? Why does this break down? Why is there not 1024?
The Shannon theorem.
Yeah, the Shannon channel capacity, the signal to noise ratio. Okay, so also look at what, if you look at the topology of these of the thing on the left, right, in polar space, right, it's shown, it's plotted in you know in orthogonal space, XY space, you know, real and imaginary part. Okay, but what fundamental principle do you see playing here in terms of the bits? What shape are these 16 bits, 16 characters?
Can you ask it another way?
Okay. Okay. According to the Shannon channel capacity, okay, signal to noise ratio is going to cause one character to be flipped to another character. Okay. How much noise do I have to add to one? Pick a circle in your mind and add some noise to it. At what point does the character shift? Right?
At the
It's a
half,
half a
halfway.
distance,
Yeah.
halfway to the next one. Okay. And so the more you spread these things apart, the less likely, just like with this, when we did just amplitude. Okay. Let's see if I can try to draw again. Still can't draw. Why can't I draw? Maybe I got it. Maybe it's yeah, it's okay. Why doesn't it let me draw? Anyway, okay, stop. Escape. Okay. Draw. But when we did the Shannon channel capacity and we talked about the noise level, what did I do when I drew the noises? I had them equally spaced. So when we did the table shapes, we talked about a single amplitude, and we had multiple encodings, right? We purposely separated these encodings, you with me? Equally spaced. I don't know if you remember this picture when we did the Shannon channel capacity. We equally spaced them, okay? And here in this example, I don't know if they're equally spaced, but they are spaced far enough apart. So if you tried to go to 64, you're going to have more rings and more dots per ring, okay, which would make them closer to each other. All right, that's my point here about that one. Okay, so here are the like I said, it frequency hops, and the frequency hop spread spectrum hops over 79 channels every 400. Okay, so these are all mitigation techniques for interference with other devices. Okay, so the direct sequence spread spectrum takes a bit, right? Takes a single bit and is going to actually transmit that bit 11 times, but it's going to take a pseudo random 11-bit random sequence, which is pseudo random, not random, but pseudo random, and then XOR it, multiply it by this generator, this pseudo, and then send it out 11 times, high and low and low and high and high. You know, the lows become highs and high become lows 11 times. And on the other side, it's going to obviously read it 11 times and recombine it. And some of the bits are going to get messed up. But if you send it out 11 times, to get the right bit, really all you need to have is, 6 of them to be arrive safely. So if 5 of your bits get corrupted with interference, but 6 of them get through, then it can recover. Okay, that's the direct sequence bits rectum. And then a technique that's not necessarily better in terms of bandwidth, but lower power and simpler to demodulate, breaks the 20, remember there's 20 megahertz bandwidth width of a channel, breaks it up into 52 subchannels, okay? And then it uses a modulation technique with an FFT and a demodulation technique with the IFT to make a lower power, simpler demodulator. And here's a picture from Wikipedia of this OFDM modulation using QAM. So what it basically does is it takes the bits in series, spreads them out in parallel. So now you have n bits in time coming in, and now you have n bits in space, sends them out across 2 channels that are mixed, out of phase. I don't know how this works, but it uses the FFT, the inverse FFT. And on the receiver, it will then, using the same frequency, FCs are the same, and the 2 out of phases, it can then recover it. So basically it is a way to send multiple bits at different times. I mean, at the same time. But apparently this demodulator is less power and less complicated. Not that I actually understand how it works. Okay, because you're using, remember the subchannels, right? The FFT allows you to see the right. Remember these 52 subchannels, okay, are now observable by doing a fast Fourier. This is where the 52 subchannels are created, and over here is where the 52 subchannels can then be reconstituted. The point is, there are lots of modulation, demodulation techniques all in this same space. It's it's a good thing we don't have a air sniffer, because these things don't look like signals anymore. But there's a picture out of the book showing again the 56 sub values. If you were to describe okay, so here I guess that we should have zoomed way in, but I do believe one of its advantages is it's not because of the fact that you're using the different frequencies separate from each other, that it doesn't have as much, it doesn't spread, right? Because you're only generating, because this output here is only generating a signal at that one frequency, you see. And so you're not causing, you're not spreading out to the other frequencies. So it doesn't spread from one frequency to the other. So in other words, it doesn't overlap into anybody else's space. All right. If you thought that was complicated, this gets even more complicated. And in order to, you've ever seen an access point with 2 antennas?
Yeah.
Yeah. And so way back when we did this and, in the fundamental theory, we defined multipath as if you radiate from an antenna, from a transmitting antenna to a receive antenna, that waves reflect off of objects, get absorbed, and therefore to go around an object, it has to bounce once or twice. And therefore, if you have a single antenna transmitter and a single antenna receiver, that there is more than one potential path from transmitter to receiver. And if those paths are different lengths, then they could arrive at different times. Okay, so and that used to be a bad thing. Okay, and so that was essentially the definition of fading, and that is as it bounces too many times and shows up too early or too late or whatever, the signal quality goes down. But it turns out that if you put in multiple antennas, multiple transmitters, and now you have multiple outputs, and you sort of intentionally send the data in two different paths because you got two different transmit antennas, and therefore by definition you have two different paths. And so this creates, just like in this one here, okay, how did the direct spread spectrum solve interference? By sending the same bit 11 times. Okay, well, over here we're going to reduce distortion by sending the same data on both antennas or on all the antennas. Okay, so if we send it out on two antennas, and now we have twice as many choices. So now you have multiple inputs because you got two antennas, and multiple outputs because you have different paths. And that's this, as some of these protocols use this thing called multiple in, multiple out. But you can also increase the bandwidth if you got multiple antennas by sending different outputs on different antennas. If you're trying to go faster, you can send multiple. And so this one here is an 802.11n, which specifically sends 4 different antennas. And then you basically are space multiplexing. Now the book talks about single user and multi-user, and I'll be honest with you, I don't know the difference. But basically here, in order to improve bandwidth here, we're going to simultaneously send data on 4 different antennas. This was this is again another multiple input, multiple output for the purpose of improving reliability. So here we're sending the same data on 2 different transmitters, and therefore doubling the chances that the receiver can reconstruct. Okay, that's the same slide. I messed up. Sorry, that's just the same slide. All right, so going down the rabbit hole, that was the antennas, the physical layer. I don't know if there's anything in here you got to remember forever, except again, the bits are encoded as QAMs or whatever, 16 QAMs, and sent out at the frame rate. And the purpose of the preamble is to get the receiver to sync, right? Because the poor receiver don't know how you're talking. And so it doesn't know when you're going to start talking. And so to get the receiver to sync to the transmitter, there's typically a preamble. And then again, this is the physical layer is all of the modulation, and on top of that is the media access control. And I've got some, yeah, there's the header. This is a Mac 802.11 header. There's a list of these bits on the next slide, but there's also the frame control bits. We got address bits, more bits, and more address bits, and then obviously it comes to the body. We're going to have we'll have a lecture on the cyclic redundancy check. Not today. I didn't write it yet. Coming up. But let me just delve into some of these other fields on the next slide, and that is these are the frame control. This thing down here, this FC. These are the frame control bits. The protocol version, the type, the subtype. You remember there was distribution system. That was the thing with the multiple access points. Some of the frames are so long it has to be broken into more frames, and so the more frames bit is set if more frames are coming, and the more frame bit is clear on the last frame of a multi-frame packet. If it crashes and wants to resend, there's a I'm encrypted, I'm not encrypted bit. Some of these things require strict ordering. So as packets get lost, they have to be restructured. And then we saw there were 4 different addresses. We got the destination address, the source address, the station address, right? Which one is transmitting and which one's receiving. And then the sequence control. That is the order, right? So that's a 16-bit thing that's ordered, 1, 2, 3, 4, 5 as the frames are sent, okay? Because somebody has to resort them eventually to the higher level. Yeah, so I'm done with this one. The next particular slide is, I probably do CRC next, or I'll do client server next, depending on how much work I get done. So this is after the exam. Then we got some 3100 demos to do. I've got a desire. I haven't written the slides yet, but I haven't written the slides yet, but I found it, and I don't know if it's going to work, but I'm going to try it again. And that is create to you. Yeah. Well, yeah, the lab talks about using the open weather map lab 3 uses openweathermap.org or IFTT, if this then that. But we've also done Wi-Fi examples where you can make your own web page. So those of you that are excited about doing some Python coding, we'll enjoy that lecture. If this still works. It worked. How long ago? The last time I did this was 2 years ago, 2.5 years ago. So I don't know. It may have totally changed. So I got to work through this, make sure it still works. To create your own web pages.
For lab 3, if we were to just stream images from a Raspberry Pi camera, would that work?
Yeah, we just got to. Okay, so okay, you can. There's an open-ended lab 3. Okay, both the lab 3 that's listed there runs on the robot and streams to IFTT. Basically, dumps data onto a Google spreadsheet. Okay, but if you do your own, you basically have to collect data with an IoT device and get it on the web somewhere. Okay. You know, it's, I don't particularly care. You've got to, yeah, you got to log data onto a cloud server, okay, to do lab 3. And you have to, during checkout, okay, you have to understand the kinds of things we're talking about today, the Wi-Fi, well, the stuff we're going to do with the domain name system, the sockets, and whether they're TCPs or UDPs, I don't care, but you're going to have to, rather than, so it all, so Austin, it really depends on how much, how down the rabbit hole you can go. One of the disadvantages of some of the Arduino ESP solutions is it obfuscates and encapsulates and hides some of the fundamental things about TCP packets and domain name serves. So, and sockets. I mean, if you can do something and you can put your finger on a socket, you know, then you're feeling, touching. So the essence of a lab is for you to understand the principles and not necessarily to create a product. So I don't care what did you're going to collect some data, okay, from a microcontroller, and then you're going to log it on, okay. So Raspberry Pi may hide too much of it for you. It's my only worry. But if your solution allows you to point to the code where you pass in a string and you get back an IP address, okay, then you're looking at the domain name system, right? If you can show where you create a socket, this function call opens a socket, and so yeah, the next PowerPoint, which I'll do after the exam, is, well, I have 2 PowerPoints down. If you just pre-look at this PowerPoint and see if you can see this happening here, right? If you can see this step happening in your lab, then I'm a happy person, because this is where the sockets are happening. This is where it opens a socket and I don't know. Yeah, no, I'm all for you doing stuff that, and so the other answer, Austin, is if it's something you really want to know how to do, then I'm all for it. Yeah. But as long as you know, during checkout, you can show me this and understand these. Yeah. I am going to show you how to make a server, but that's not necessarily something everyone has to do this semester. I mean, I may make them do it next year, but not this year. Did I answer your question?
Sort of.
Well, okay. Let me just. I have 2 hot button responses. Okay. Those of you who say, "Can I do it with an Arduino?" You get some sort of hate response. Have you noticed that, Keyshawn? You notice that?
So sometimes.
Sometimes, yeah, not real. You know, as much as a 66-year-old, you know, fluffy bear can be. And what is it I don't like about the Arduino? And that is, you know, it's basically a download and run kind of environment, and it hides some of the fundamental details of how stuff works. I mean, yeah, try to do an analysis of a critical section in Arduino code. Yeah, I don't know. I'm not sure you can. Try to make Arduino real time. Right? You know that, Austin. You can't. You know, on that fun project we did with Abu and the low cost respirator. That code that Arduino code really never established a sampling rate that was reliable. Now with a Raspberry Pi or a BeagleBone or an Atom, you get another set of, hate's not the wrong word. It's really a perspective. A Raspberry Pi is a portable laptop. It's a portable personal computer. And so Raspberry Pi, if you use the word image, then you must use a Raspberry Pi. You couldn't possibly image onto a TM4C or an Arduino or a MSP432 or MSP430. Okay, you can't do images on a. You have to go to a Raspberry Pi. But now you're running in Linux, and which is not real time. And I don't have to. It doesn't have to be real time. But again, you're also into an environment where there's so much code, which you shall use because you're a grad student, but you must understand. And so that's really my answer to any of these labs, regardless of the platform you use, and that is to make sure you can delve down and understand the essence of Wi-Fi. Okay. Yeah.
Okay.
Yeah, no, I am less hateful towards Raspberry Pis or BeagleBones and that kind of thing, because that's real stuff. It just its perspective is very different than what you do with a MSP 430 or an M432 or a TM4C or a Teensy or a Arduino or the CC20, whatever, CC, pick a letter number. Those are embedded controllers. Yeah, I took $30,000 from Intel to launch an Atom into the space, well, into the air. I don't know if you've ever seen an Atom board, but it was essentially a laptop motherboard, which just the board itself took an amp to run. But we got a big enough drone battery and a big enough drone engine to get an Atom to fly. It didn't fly very long. It was totally the wrong microcontroller to do drones. But if you say I want to stream images, then the Raspberry Pi is the correct one. Yeah, or BeagleBone, or telephone, right? Any other questions? Specifically, any questions come up about the test? Okay, I'm not. It's my plan is for you to enjoy it. How's that? Think that's possible? To make a question you'll enjoy doing?
Not if we have to copy and paste images.
I second that.
Okay. Well then,
Potentially. I mean, I don't know.
okay. Well,
The main thing that worries me is you're just adding a breaking point or something that could go wrong.
no, I get it. You will have the option. How about this? You will have the option. Okay, go up in process, under process. How about this? Just reduce your fears?
Yeah.
Okay, so what if you get out a pencil and a piece of paper and you draw me something and say, this goes with question 2, you get out your phone, take a picture of it and email it to me.
Yeah,
How's that? Feel better?
yeah, I'm happy with that.
Okay, yeah. Because it's not about technology, it's about content. Yeah, and so
Well,
you
the
might,
content is sort of technology. So
yeah, but that's not the point of the exam, right?
Yeah.
Copying and pasting pictures. I mean, this is not a whatever a class in technical communication. It's a class in IoT. So yeah, as long as I want the right equations and the right. Yeah, the same thing. Sometimes with equations, it's a little easier to draw them with the square roots and the subscripts and sure. No, you'll you'll have the.
Do you have time for a lab checkout later today?
Okay, what's today? Today is Thursday. Okay, so let me stop sharing. Ooh, today. Today. I'd rather not do it between now and 12:30 because I haven't prepared for my other class, and I shall. Okay, today's the 22nd. Okay, I have okay, so 3 o'clock, 4 o'clock, or 7 o'clock.
I'm with Austin and I have class at 3:30. So we could do 3
Okay.
as long as it ends before 3:30.
Okay, so we can do 2:30. We'll do
Even
2:30.
better.
Yeah, that works.
So let me put a let me go over here. Okay. Anybody, while I'm setting a Zoom situation, does anybody have any other questions? All right. Schedule a new meeting. Okay, check out lab today, 2:30. 2:30 p.m. All righty, waiting room now. Enable join our host. Save. Okay. Start. No, edit. Okay, now edit the meeting. Here's my. Save. Start. Oh yeah, there it is. Copy invitation. All right. So, are you still there? Would be better if I put it in the chat, or should I email it to you?
Email. I'm still on.
Email.
All right, so we'll go email. Good morning. All right, does anybody else have any question? Otherwise, you may. Okay, so I'm going to new message. Okay, so that was Austin and all right,
In Jackson. In
Jackson.
Jackson.
Jackson. Jackson Farley.
Sure.
Is that you?
Yeah, that's me.
Okay, fine. I just typed Jackson into my email.
Yeah.
Okay, 2:30. Paste. Send. All right. All right. Be safe out there. I will have office hours between now and Tuesday if you have an exam question you want to ask. Yeah, but so Austin and Jackson, upload your lab thing. So that's what I usually do. I start reading your